Hello. In today's session, we'll be looking to learn linear regression using Python. And the purpose of this video is to make sure that we learn one of the models. That is, there are several models like linear regression, there is lasso, then there is ridge, elastic net, and a couple of others. So our goal is, if we can understand one of them clearly well, it makes learning for the other models relatively easier. So with that attempt, we'll go into explaining how linear regression works. So this is our agenda. We'll first look at the use cases. That is, we know we're going to learn linear regression, but where can it be applied? And then what is contained within linear regression? Like, what are the equations for it? And what is the cost function? How the graph looks like? What is the slope, intercept? And finally, when we are done with all the basics, how do we evaluate our model? So there are like two ways of evaluating our model. One is R square and the mean square. So what does it mean? And finally, we are going to walk through the code. And the code is also available on GitHub, which is shared at the end of the slide. So you can actually go on and try it out as well. So going to the use cases now. Linear regression has been applied in a lot of areas, starting from simple ones to complex ones. Simple ones in the sense, for example, let's say you have a value of heights and weights, and you can train your model giving this data, and you can ask your program to predict a weight given the height. So that is one use case. And the second simpler one is an ice cream shop. Like they can make a decision, like, given the temperature, how is my sales going to look for today? Or they can do it for the beginning of the summer versus end of the summer, typically to predict sales. And on at a medium scale, for example, a marketing department in a company which has been running ads on radio, TV, and online, can predict what sales is bringing more revenue and focus more towards that advertisement medium. And linear regression finally can also be applied to complex cases, like a car insurance company, or for any insurance company for that matter, can apply linear regression to predict the premium table, at how much you'll be paying month after month. And they can do it based on the predicted claims of the IDV value, the insured declared value. And they can come up with that value based on several factors, which can be taken in by the algorithm to process it. The information can be like, what are the attributes of the car? Is it like a car that can drive really fast, like a high-end car? Or the age of the driver, the demographics, where he comes from, what city he drives. So based on all that information, the insurance company can come up with the payment table. So jumping into what linear regression is. So linear regression is pretty simple, as mentioned in the use cases. We have a target value. A target value in the sense it is something that we are interested in finding out. And in order to find that, we need to train the model. So it has two values, X and Y. And let's assume that X is the value that we have, and based on the X value, we are trying to predict the value of Y. So we are basically trying to see the relationship between these two variables. Is the increase in X increasing Y, or the increase in X decreases Y? Those kind of basically the relationship. How are they positive or they negative? Things like that. And it is if you talk about linear regression, there are like two types. One is a simple linear regression, which means you have one X value and you're predicting one Y value. That's it. In the case of a multivariate linear regression, you have multiple features, which could be x1, x2, x3. There are several features, which, for example, in our use case, you could go back to the advertisement medium of radio, TV, and online. So if you take all three, and then the final Y is your sales, That is your multivariate linear regression, where instead of like having 1x, 1y for a single simple linear regression, you're trying it out on multiple features and you're trying to predict one value out of it. So that is multivariate. So these are the different two different types of linear regressions. And this is an example that I just briefly mentioned a couple seconds ago. So where in this case, we have a simple case where we have one X value and this is one Y value. So this is the case that this is an example that we are going to take for our code also and run the model and do some predictions. For now, the X and Y, there's just some random variables, and in the actual code, we have 700 of them, and we're going to make our predictions based on that. So whenever you take these into consideration, a typical prediction, what it'll do is it'll try to plot these X and Y values on a graph. So if you see the X-axis, as you know, it is the horizontal one here, and the Y-axis is the vertical one, and the points in between are like, if for example the first one, X is 24 and Y is 21.5, so which would be the X value of 24 could be somewhere over for this point 24, and the Y value of 21 is here. And if you take the second value of 50 and 47, so it could be this one, this value here. Similarly, we plot all the 5 points, and once we plot all the 5 points, we draw a straight line through it, which is called the best fit line. So what the best fit line means is, you have to find, the algorithm will find a line for you that will try to accommodate as many points as possible. But we need to remember that not all the points are going to stay on the line. There are some points that are going to be above the line and below the lines as well. And we will have to factor that as well. So we'll be in the coming slides, we'll try to see how we are going to evaluate those things. So for now, it is simple that we had take the X and Y values, we plot them on the graph, and then we try to fit a line. So this is not manual work, this is automatically done by the model, but this is just an example. And for linear regression, this is a typical equation for linear regression. And it goes as y, which is our predicted value. We're going to predict this value of y, which equals to a0 plus a1x, where the a0 value is the intercept and the a1 value is the slope. So what that means is, so if you see here, this is the slope. The slope can be like here, or it can be too steep as it goes over this line, or it can be coming flat towards this side, toward down. So this is the steepness of it, which is the A1 value. And the A0 is actually the point at which, if you extend this line a little bit, the point at which it crosses the Y or the X. So that is our intercept, which also means Y intercept. So this is all about the equation. And this is also, some of you may also be familiar with this equation as y is equal to mx plus c, where m is the slope and c is the intercept. So our goal is to find the best prediction values for A0 and A1. And once, as I mentioned before, so once we draw a straight line, there are obviously going to be some points, right, above and below the line. And what we have to do is, we need to take those points that are above and below, and we have to calculate the error function or the cost function. Cost function is, it tells how far the points above or below the line are away from the best fit line. So we take some calculate and it takes a measurement for each of the points that are away from the line, and then we calculate something called a mean squared error. So which we'll also be going in the coming slides. I'll tell you how to calculate mean squared. So this mean squared error is going to tell us how good our model is. So is our model really good? Can we take it and use it? or we need to make some couple of tweaks or make some adjustments, or maybe the data it does not showing any relationship. So those are the things that we are going to do. So cost function is basically, it tells how good your model is. That is the best fit line, how best fit the line is. So here is another visual example that shows the best fit line going. And if you look at the y-intercept, the point that this line touches the y-axis, that is our y-intercept, which is also known as a0, or in the example of y is equal to mx plus c equation, it could be your c value. And the steepness, this is called the slope of it. So this is actually the m value or the a1 value. And if you see here, there are some points. Obviously, there are some points along the line, and there are also some lines, some points below this line, and some points above this line. So the distance, if you measure the distance between these lines, right here, over here, and this distance, so this is what we use for mean square calculation. So calculating this difference tells how far our line is from the other points. So that is what we are going to look at. And here are the real values that we have been using, that we will be using in our code later. So these are a couple of x values, and these are the y values that have been given to us. So this is what we have, where x is the independent variable and y is the dependent variable or target variable. Okay. And this is when we run our model, we get these two values, the intercept value and the slope value. And using these two values, we are going to see how our prediction looks like. So we are actually, what we are trying to do is we are trying to do a combo where we have the data and then we run our model, we generate the equation, we take the values in, and we are going to compute the y predictions manually here, just to give you an understanding. So what happens is, as I said, these are the x values, these are the y values that have been given to us, and these are the y predictions that our model has predicted. So if you look and compare both of them, right here it is 21.54, but whereas it's 23.897 here. So we have a difference of almost 2.3, which is the difference between the actual and the predicted. So we note down the difference here. And similarly, we note down the difference between this y value, the actual one, and our prediction. And we calculate all the differences here. And let's ignore this column because it's kind of irrelevant. So once we do that, if we square this value, we are basically squaring this value to get rid of the negative signs, which is in the last column. So which is y minus y, predicted y square. So if you square it, these are the values that we are getting. And when you add everything, when you take an average of everything, that is your mean square error, which is here. So mean square average is nothing but the average of whatever we are getting here. Now you might be wondering why we have to square these values. We could have actually done without squaring the values itself. This is also one way of taking a distance. But what this distance specially does is, when you do a square, if you have a smaller value, squaring it will become extremely big. So if you take this value here, 62, which is the actual difference, but when you square it, it becomes close to 4,000. So what this means is, when finding a mean square error, we are penalizing the differences so much to highlight them well. This will make sure that our model, this penalization will ensure that, okay, this is too high, so I need to come up with another best fit line that can lower my value. So the goal of the algorithm should be to give you a value that is so less for mean square that your model is good. So that is basically the idea behind it. And there is also another one called root mean square error, so which is basically the square root of mean square. Okay, so based on the value, one more point to add, based on the value that our program gave, resulted, that is the intercept A0 and A1 value, we can come up with our own equations by substituting it in the actual equation. So substituting the value of A0 with the value here, which is a negative 0.1201, and a plus A1 value 1.0007 times x. This x is actually xi, which means when calculating the first one, right, you do that and then you multiply it with the first x, 24. So you get this value for y. So when computing the second value, you take the 50 and feed it to this xi here, 50. So when you similarly you do it for all the others, and this is how you end up getting your y predictions. So this is basically about how you, if you want to do it manually, this is how you do it with help of the model to get your intercept and coefficient, and if you want to work it out manually to get a better understanding. Now remember that the code is going to do everything for you, and I am explaining it out a little expanded so you get the idea for how the calculation for mean square error works. So as I mentioned, this is again the equation, which is y is equal to a0 plus a1 times x, which is our xi values. And then with the values that we obtained here, this is how our equation forms up. And what this equation tells us is for a unit value of x. So imagine when you substitute x with the 1, right? So it is basically negative this and a positive this value, which is 0.88. Now when x becomes 2, your y value is 1.88. So what this is telling us is for each value of x, how much is our y value impacted? That is all it's saying here. And finally, we are going to evaluate our model. What is that? How can we evaluate our model? There is a matrix called R square that we can use. It when we run the matrix for R square, which is similar to mean square error, it will tell us how close the points are to the fitted line. And it also tells that what amount of variation in y can be explained by x. So the higher the value of R square, the better our algorithm is. So R square value is always between 0 and 100%. So the higher it is towards 100%, the better it is. So 0% indicates that the model cannot explain any variability in X for the given Y. So key limitations of R square. So what are the limitations of R square? R square is good. It gives you the basic understanding of how efficient it is, but it cannot tell us how biased the predictions are. When I say biased, in the sense, sometimes what happens when you use an algorithm to do some predictions, it understands your test data so well that it will work good for that one set of data, and the moment you give it new data, it can find a good prediction. So that is what called biasing. Biasing, it's more biased towards the set of data that it has been trained. So R square value will not tell us if our algorithm is, if our model is biased or not. And the mean square error, as I explained earlier, mean square, it tells if you remember the chart here, the mean square error is basically calculating the distance between this line and the plots here. So we take the difference between each of these points, and when we square them, and then we take the mean of them. Okay, so this is the example that we use to get both the values. So we are evaluating our model in two ways. One is R square and MSE. So in this case, our mean squared error is 398.865. So we are to the final part of it, where we are going to walk through the code and get an understanding how linear regression works. So the first few lines, if you look at all the inputs, these are loading the binaries that are needed for our model. So the first library, if you look at, maybe some of you are familiar, but I'll just run through them a little quick. So the pandas library is used to load your CSV files, and NumPy is used for some arrays that we are using. And this library is for bringing in the linear regression model. And the R square and the mean square are for calculating the metrics, and PyPlot is for plotting our results on a graph. Okay, so these are just like the first few lines are the libraries that we are loading. And then these two lines, what we are doing is we have this data in two files. One is called the train, another one is called the test. We are going to use two files because when we initially teach the model, that is train the model, we are going to give it only the training data, and then we are going to ask it to predict it based on the values on test data. The reason that we are doing it is it's like us learning something and then appearing for a test, just like kids. They're like learning something and which may not cover everything that is going to come out on the test, could be slightly different or a different variation of it. So similar to that, our data is contained in two files because we are going to not show our test data to the model so it can test it, it can do the predictions well without getting any exposure to it. Okay, so now in this place, what we are doing is we take all the training values and test values and move to the required variables. That's all. So we have like 4 variables. X train has the training values of X, and Y train has the training values of Y, and X test has the test X values, and Y test has Y test values. Now, after doing everything, we are converting them into arrays using the NumPy. So when we convert them into array, you see these are like all one dimensional, and we are going to have these two lines of code to convert them into two-dimensional values. We're going to reshape them to convert them into two-dimensional values. And finally, this is the 3 lines of code. These are the most important. This is the meat of linear regression. What the line means is, first we are saying we are going to create an instance of linear regression, and we are giving it a parameter normalize is equal to true. So this is optional. Even if you remove this line normalize equal to true, it works completely fine. But what normalize does is it takes all your values and it brings it into the range of 0 to 1. So the weightage for all the individual values is the same. Okay, that's all the first line does. The second line is, this is where we are training our model. So when we train our model, we are giving it the training values of X and training values of Y. So we are saying, go fit it in the training values. And then this entire 2 lines, it is going to train our algorithm. Once this step has completed, our algorithm is ready. Now we're ready to do our predictions. So what we do is, so we run our predictions, but remember, just on the test X values. We're not going to show our real Y value here. We're basically in this line, what we're telling is, hey, I have given you some training data of X and Y values, and I am just giving you some test values of X, and I want you to predict the values of Y, and I'm going to collect the predictions in Y underscore pred variable. So that's all the 3 lines. These 3 lines are pretty much like almost 95% the same for majority of the models. That is, you will create an instance of it, you will fit it, and then you will do the predictions. So if you understand these 3 lines really well, then you can read through all the other ones and you can work your own examples. You don't need to get a full course to do it. It's pretty much easier, self-explanatory, if you understand this one model really well. Okay, now that we are done with it, we are going to evaluate it. So to evaluate it, remember in the Excel sheet that I showed you earlier, we were calculating all the values one by one, but here we can call a library, and we can pass, okay, here I am passing you my y test, that is the actual y values, and my predicted y values. You take these two and tell me what is the mean squared error. And similarly for r square, we're saying like, okay, hey, I want to find out how much of the value of y, variability of y, can be explained by your x. Give me those two predictions. And then we can also say, give me the intercept value, which is the a0 value, and the slope value, coefficient, which is called a coefficient here, the a1 value. So we're printing out all the results here. And then we can come up with our own equation. Though we don't need it, we are having it here just to see how an equation that you formed will look like with the substituted values. Okay, and this is the final part of it. So now that we have in the code, we have walked through loading the libraries, and then transferring the values to the loading the libraries, then reading the CSV files, moving the variables values to the variables, and then training our model, predicting the values, and then calculating evaluating our model, the R2, that is the R square, the mean squared error. And now we are going to plot our results on a graph. So in order to plot it, we are using the matplot library, and we are going to scatter plot it. When we are going to scatter plot, what we are giving it is, hey, I'm giving you the test values of x and y. So scatter plot it. These are the actual values. And once I have these actual values, what this line tells us, now you have the actual values of test x and y here. Now I want to plot it with the test values of x, but instead of the actual y, I want you to run a line with the predictions that I made. So it will look something like the one here. So if you see all the gray dots here, right? These are the actual test values, the gray circles, filled circles. And this red line going through it is our best fit line. So this is how the graph appears for us. So going back to the code, so this is what it tells. So color this gray, that is plot my x test and y values and color them gray. And then run the best fit line using my x test, but instead of the actual y, run it with my predictions. So I want to see how my predictions are close to the actual y values. And I want it in color red, and with the line width of 2, which makes the red line a little thicker. So if you want, you can, if you remove it, look slightly leaner, that is all. Or you can, if you want a little larger, you can say line width is equal to 5. It's up to you. And then we are giving a name to our x-axis and y-axis. So you can give a fancy name or keep it simple. So for our demonstration purposes, we have just named it x-axis, y-axis. And the final line here, it shows, okay, show me the graph now. So without this, your graph won't show. So this line is equally important. You can have all these 4 lines here, but without this, nothing's going to show up. So finally, you have the link here. And this link is our GitHub for where the code is. You can take the code and run it, play with it, make some tweaks, and try to get your understanding of it. And this is the final graph. As I said, it's got gray lines, the scatter plots here. And we have our best fit line in red here. And then finally, the name that we gave for our axis, the x-axis and the y-axis. And this is the output that we get from our graph, along with the R square and mean square value, which you can find out when you run it. So with this, we have come up to the conclusion or middle. Hope you liked it. You might have got a good understanding of linear regression. If not, let us reach us out and tell us if you have any questions, or feel free to reach us. Go on our slide or go on our website, GoGuru.com. We have a couple of videos that we share from time to time. So read through it and reach out to us. Thank you. I'm Jay Kumar from GoGuru.com.